Thanks. I have an announcement too. So for this lecture, I decided to have some interactive sessions. So I want you to do some calculations on paper. Does everybody have papers? So that's good. And if you don't have, you can ask your neighbors to see if they have extra. And so I have tried to give you some introduction to QCD factorization in a previous lecture. And if you do not remember anything, that's okay. It doesn't affect this one. Can work? Yes. So what we have seen from the previous lecture is we factorized the DRS in terms of a hot part and a collinear part. And the DRS factorization is actually the simplest one. And that's why I use this as an example. And it's simple because we only have to worry about two different momentum regions. One is collinear, one is hard. And the goal of DRS factorization is to factorize all the collinear pinch singularities from the hard interactions. But in reality, we have a hadron colliders, and hadron collider produce an important process that we call Zhite process. What Zhite process is, you have a collision of two hadrons with momentum PA and PB, and in the observable, you observe a lepton pair, like a muon pair, mu plus, mu minus. And this muon pair carries a large invariant mass. I denote it as Q. And you can imagine that this muon pair is created by a virtual photon of high virtuality of order Q. So it's still dominated by the hard region. And in this case, we also want to factorize this process in terms of two PDFs, one with PA, one with PB, and the hot part as denoted here. But the complication is we have two collinear sectors, and this PA and PB move in opposite directions. So they can be connected by a number of soft gluons. And this soft gluon is something we have not seen from DRS diagrams. And there are a great deal of complications associated with the soft gluons. And I will not have time to explain all these details to you. I only want to point this out that the factorization for the Zhite is more than the factorization for DRS. We not only want to factorize the collinear from the hard, but also we want to factorize these two collinear factors, one with PA, one with PB. They should be separated from each other. And they are individually factorized from the hard part. And furthermore, we want to make connections between the PDFs factorized from Zhite to the PDF factorized from the DRS. We want to show that they are the same. And the factorization formula, as you have probably seen before, it takes the form of the convolution of two PDFs and the hot coefficient. And the process for the procedure for factorizing this is very complicated, and a great deal of complication associates with this cancellation of soft gluons. And the technique for using that is to see that the final state observables is only the lepton pair, but plus anything else. You can allow anything that happens at the same time with the production of this lepton pair. And therefore, we can use this inclusiveness to sum over all possible states. And that is called the unitarity argument. And that argument will cancel all the soft gluons. And in the end, we also managed showing that the PDFs from the Zhite are exactly the same as the PDF in DRS. And that is what we call by universality. And similarly as DRS, the hard coefficient can be calculated to any arbitrary perturbative orders, but you have to carefully subtract all the collinear pinches. And therefore, the resulting hard coefficient is infrared finite. I will not go further for the discussion of factorization. I just want to introduce you to the Zhite factorization and also to give you an idea that there are multiple processes that have relations to PDFs. And that leads to the global analysis of PDFs. And the starting point, as I have just told you, is that the PDFs are universal. They do not depend on what processes we use. So they can be studied at DRS, it can be studied at Zhite, and it can be studied as a few more other processes. So we can parameterize them in a certain way and fit them to all the data that we can have. So the starting point is we parameterize the PDS at a certain chosen scale that I call mu naught. And you can parameterize this in principle in whatever way you want. But the typical way is to have the form of x to the power times the 1 minus x to the power and multiplied by a polynomial of x. And this example is given by the GEM20 cities parameterization. And this parameterization should be done for each flavor, each parton flavor of the proton or any other hadrons. The index I denotes a parton flavor. It can be gluon, can be up, downstream charm, and their anti-quarks. So if we stop at charm quark, here we have 9 independent flavors. So you can imagine you have so many flavors, and how do you constrain them? You have to include as many processes as you can. And then you use this parameterization, you want to make predictions for observables. But observables are not necessarily at the scale mu naught. So you need to use the de Graaff evolution to obtain the PDF at the scale Q, which is relevant to the certain processes you are trying to fit. So you use this to evolve the PDF, and then you use the factorization formula to make predictions for the observables you are measuring. Say in DRS, the observable is the structure function F1, and we use this factorization formula, the PDF here, and there is a hard coefficient. What can change in reality is the perturbative order of this hard coefficient that you calculate. And then you compare that with the experimental measurements. Experiments have uncertainties, and theory predictions have uncertainties too. So in this case, by this comparison, you design a certain loss function, like a chi-square. And this chi-square depends on the uncertainties of both theory and experiments, and it's a function of the parameters in this functional form. And then you tune this parameter to minimize the loss function to find the best fit. And the major complication in this business is to quantify the uncertainties of your result. So if you work on the global fit of PDF, you will spend most of the time in the first step and the last step. But if you don't work on global fit, it's better to have some idea about what's going on. And the common things to no matter what you do is this intermediate 2 steps. You solve the de Graaff evolution and you use factorization to make predictions. And we already talked about how this factorization is derived. And then we will think about how they are applied in reality, in phenomenology. And for this lecture, I want to introduce you to the great phenomenology of de Graaff evolution. And I hope you will be convinced in the end that we actually gain a lot by analyzing the behavior of de Graaff evolution equations. And let's recall from the previous lecture, I have briefly said that the de Graaff evolution arises from the UV renormalization of the PDFs. The PDFs contain UV divergence when they are factorized. And this UV behaves like a hard blob. And this is factorized from the collinear part. And then the upper part collects all the UV divergence, but the lower part is a renormalized PDF. And this happens in a multiplicative form. So I have this multiplicative renormalization. On the left-hand side, we have the renormalized PDF. On the right-hand side, we have a convolution form of this bare PDF. This contains UV divergence, and this UV divergence signified by the 1 over epsilon poles in the dim red is collected or cancelled by the renormalization constant Z. And this is a multiplication in the flavor space. Ij denotes the parton flavor. And this renormalization factor can be perturbatively calculated order by order. And because it's only a property of UV, it should concern only the momentum scale at a very, very high scale. It does not care about what target you use, the target carrying momentum P. It doesn't care about the mass of the partons. So therefore, if we only care about the renormalization constant Z, we can replace the target by an elementary target, a parton state K. Both all these ijk can be either quark or anti-quark or gluon, and we have the same formula. And now we want to understand a few symmetries for this renormalization constants. The way to do that is we notice that the renormalization constants are UV divergence properties. And therefore, if we look at the bare PDF, the bare PDF has a symmetry, the charge conjugation symmetry. So the parton I from the parton K should be the same as the parton I bar from the parton K bar. And therefore, their UV divergence are also the same. And that implies that the UV renormalization constants are also the same if we just replace the partons by antipartons. And that also implies that for the renormalized PDF, if we replace the partons by antipartons, they are the same. And therefore, we write down the evolution equation or the DGLAP equation. The DGLAP kernel is basically a derivative of the UV renormalization constant with respect to the mu square. And the kernel should also be the same if we replace the partons by antipartons. And that is the first symmetry we obtain for this DGLAP kernels. Or I will refer to the Pij as DGLAP kernels. And we have seen the charge conjugation symmetry. And the next symmetry is we have a flavor symmetry because when we only think about UV, we can think about the partons as massless partons. So we have a approximate SUNF flavor symmetry. NF denotes the number of active flavors in your in the problem we are looking at. So the first thing we can see is if we look at the quark from a gluon and anti-quark from gluon, these two should first be the same by the charge conjugation. And then it should not care about which flavor the gluon is splitting to. So it should be the same. It does not depend on the index I. So we denote this as PQG, the first kernel. And the second one is for a quark to split into a gluon, it should be the same as the anti-quark going to a gluon and should not care about which quark flavor it comes from. So it's also the same kernel, PGQ. And then for other kernels, for quarks splitting into other quarks, and anti-quarks splitting into anti-quarks. For example, we can have the D quark to U quark. This should be the same as the D bar to U bar. And by the flavor symmetry, it should be the same as from the strange quark to U quark. But it may not be the same as the splitting from U quark to U quark because these two flavors are the same and these two flavors are not the same. And similarly, we have the splitting from quark to antiquark or antiquark to quark. These two should first be the same and should not care about the flavors you are splitting to, from strange to U bar or strange to D bar or D bar to U bar. They are the same by flavor symmetry, but they may not be the same as the splitting from U bar to U. And these are the basic intuitions. And based on this, we parameterize all these various deglab kernels by 7 independent kernels. First, let's look at the simplest one first, from the bottom to up. The bottom to up, we have the gluon to gluon splitting, and we have the same one. This is not constrained by any symmetry. And we have the quark to gluon, antiquark to gluon. This gives us the same kernel, quark to gluon. We have gluon to quark and gluon to antiquark. They are the same, and they give the same kernel. But now, if we look at the first row, the splitting or the evolution kernel from quark to quark, and there is the flavor indices I and J, and this is first the same as the splitting from antiquark to antiquark. But then we parameterize them based on the previous wisdom. We can have a common one, PQQS, which does not depend on the which does not depend on the flavors. And we have another one, which is there when these two quark flavors are the same. So the first term contains the delta function, and second one does not care about the parton flavors. So that gives us two possibilities. If I equals J, we have the PV plus PS. If they are not the same, we have PS. And the similar thing happens for the evolution from anti-quark to quark or quark to anti-quark. We have similarly two kernels, PV from Q to Q bar and PS from QQ bar. And here, the subscript, superscripts, the V and S denotes the valence or C. And you don't have to think much about why they are called that way, and you will get the idea in the end. So now, we can use these 7 independent kernels to rewrite the deglab equations. And to simplify all this notation, I introduce the abbreviation. If the convolution between A and B is just, it just means this, and this has satisfied association law. And for labeling the flavors, I use IJ to label the quarks, UDS, and I bar and J bar to indicate their anti-flavors, and the G indicates the gluons. So for the evolution of quark PDF, we have 3 terms. The first term is the mixing with other quarks. The second term is the mixing with anti-quark. And the last term is the gluon. And similar thing is for the anti-quark PDF. We have the mixing with quark, mixing with anti-quark, and gluon. And the last term is the gluon. We received contribution from quarks, anti-quarks, and gluon. And then you apply the parameterization here to reduce all these equations. So I want you to do this exercise, and I'll give you 4 minutes to reduce these 3 equations by taking the parameterizations here, because the parameterization reduces all these kernels into 7 independent ones, regardless of their flavor indices. So take that and reduce these equations. Yeah, originally I was planning to write this on board, but we only have a small board. So to be more effective, it's better that you carry out this exercise by yourselves, and then you'll get some feelings about what I will talk about. And you may be wondering why you are doing this, and you get that in a minute. Feel free to discuss with your neighbors. Okay, so time's is up. It should not be so complicated. The only complication arises because you have to write down a lot of terms. So if you have not finished, that's okay. I just want you to get some idea what is down here. So we put all these independent kernels into this kind of equations, and you see that they decompose. They decompose into these various terms, which has some disentanglement in the flavors. For example, if we look at the first term, this Pij, two term, one is the valence contribution, the other is the C contribution. But the valence term only applies when the two flavors are the same. So the first term is only proportional to Fi. But for the C term, you have a sum over the second flavors. And similar thing applies to all the other calculations, and you should be getting this. And the reason why we are doing this is to make use of these asymmetries to decompose the parton flavors of Dirac evolution as much as we can. This will be very useful if you try to solve these Dirac equations. And how do we disentangle all these flavors? We have used the charge conjugation symmetry. And then to go further, we notice that this quark and anti-quark PDF, they mix with the gluon PDF in the same way by the same kernel. And the gluons only mix with the sum of quark and anti-quark PDFs, again by the same kernel. Wait, this kernel is not the same as this kernel. They look very similar. This is a GQ, this is a QG. And the convention is the parton flavor on the right is the initial state parton, and the one on the left is the final state parton flavor. So by noticing this, it motivates us to define two combinations of the quark and anti-quark PDF. We define Fi with superscript plus or minus, refer to their sum or difference between the quark and anti-quark PDFs. So now the following task is, please use this redefined part combinations F plus minus to rewrite this de-Glab evolution equation. Basically, you derive the evolution equation for F plus or minus, and I'll give you 3 minutes. Yes?
I have a question regarding the word kernel. This is kind of something that usually appears in this topic. Kernel would be whatever goes by the side of the PDF in the de-Glab equation, or there is like a more rigorous definition.
It's just a term, right? It refers to the convolution, the factor that convolutes with PDF.
Okay.
In the convolution.
So anything that is convoluting with this non-perturbative function would be the kernel of that de-Glab equation.
Yeah. So it doesn't mean anything profound. It's just a terminology. Okay. So please work this out. 3 minutes. Right. So I hope you have finished. So if you have any question, please let me know. Yes.
What would F plus or minus G just be 0? Would that be the case then?
Which one?
Like F plus G. So for the, or would that just be like either 0 or 2 FG? What's this?
You're referring to? No, you're referring to?
Like the definition of like Fi plus or minus. If you
Fi.
get I is equal to, G for the gluon.
Oh,
That would either go to like
Sorry.
0 or
so here, I refers to the quark flavor. Yeah, because of gluon, it's meaningless for this definition, right?
yeah.
Yeah. So the reason for this definition is that by taking the plus, we are summing over quark and anti-quark, and this is called a charge conjugation even quantity because it's invariant if you apply charge conjugation. And for the Fi minus Fi bar, that's a quark minus anti-quark. That's a charge conjugation odd quantity. So it flips the sign if you apply charge conjugation. And for gluon is its own antiparticle, so it's charge conjugation even. Therefore, you should only expect that the charge conjugation even combination mix with the gluon, but the other doesn't mix with the gluon. And this is what you should be getting. If you have finished doing the calculation, you should be amazed by yourself because you have achieved a lot within 3 minutes. But let's now, if you haven't finished, that's okay. Just take a look at the result. We have obtained 3 equations, one for Fi plus, one for Fi minus, and for the gluon. For the gluon, the upper part is the same as what you have seen on the previous slide, and this is the result. So here, Fj plus Fj bar is just Fj plus, and you sum over the flavors. And the Fi minus only mix with the Fi minus and the sum over its flavors. Fi plus only mix with Fi plus, the sum over its flavors and the gluon. So by this particular form, it should motivate you to make another definition. We define the sum or flavor sum of all the plus PDF combinations as f of s. And we also define the sum over all the minus combination as fns. And this means S refers to flavor singlet and NS refers to flavor non-singlet. And you don't have to worry about the terminology so much. They refer to the flavor isospin group. But now the exercise is take this definition, Fs and Fns, singlet and non-singlet, you work out the evolution equation for these two. And you have 2 minutes. And you assume that there are NF active quark flavors in all this equation, which means the index I takes from 1 to 3 to NF. And please work this out. Okay, so 2 minutes is short. And I hope you have derived something. At least you have got some idea about what you are trying to do. By summing over the flavors, what we get is here. The first one, Fi plus. Now I reordered this a little bit. I put the first row here in the second row. You see that by summing over the flavors, summing over I, the left-hand side gives you F singlet. And this one gives you a singlet. And this term is already a singlet. So summing over itself by NF times, it gives you a factor of NF. I mean, time the same kernel. And the last term F gluon, similarly, you have a factor of NF. So this factor is it's very easily to be missed. And for the second equation, if you sum over the flavor I, you get non-singlet combination for this left-hand side and the first term. And the second term just gives you a factor of NF. So you get this equation. And the last one, it's unchanged, it's the same. So now with the singlet and non-singlet definition, we see that the first equation, non-singlet combination, only evolves by itself. So if you try to solve the equation, this can be directly solved. But for the singlet and gluon, they mix with each other, but they only mix each other. So this is the 2x2 mixing matrix, and this is a coupled equation. And this can also be solved if you first diagonalize the evolution equation and then they solve by the eigenvector. And then with these two definitions, we only get the sum over all flavors. So we only have 3 equations. But originally, we have a lot of equations because the index I can take from 1 to NF. So in total, we have 2 times NF plus 1 equation. And so we need the remaining 2 times NF minus 1 equations. And these equations are for the relative differences among all the flavors, because here, these 3 equations give you the sum, their sum. So the following equation should give us their relative difference. So with that, we define, for example, there are a lot of ways to do this, by the way. One way is we define the flavor difference between I and J. I call it Fij plus or minus, which is to take the difference between the flavor of I and flavor of J. And by the first 2 equations, you can see that if you make a difference between 2 flavors, the singlet piece and the gluon piece cancels in the first equation, and the non-singlet piece cancels in the second equation. So you get a simple equation like this. With plus and minus, you get different kernels, and they only mix with themselves. So with this, you can define as many flavor difference as you want, and you can solve these equations. And this equation is very easy to solve. Another way to do this is we define the difference as the singlet combination minus NF times the flavor we are looking at. So for each flavor, we define this kind of difference. And similarly for the minus combination, we define this as the non-singlet piece minus NF times the component we are looking at. And the same thing applies. These only evolve by themselves and by the same kernel that we had before. So then you get the result that you want. The first 3 equations are the same as the previous one. We have non-singlet, singlet, and gluon, and these 3 equations. And the other ones are given by the flavor difference. They evolve by the valence kernels and evolve by themselves. This gives us the remaining 2 times NF minus 1 independent equations. And then by solving them, you get the first equation, first 3 ones give you singlet, non-singlet, and gluon. And the other ones give you the difference between the singlet and non-singlet with the flavor you're looking at. And then converting back to or original flavor, Fi plus or Fi minus, we can easily obtain this by reverting these equations. And by this, we start being able to solve the Degrave equation. So the result is actually very beautiful because we start with the fully convoluted mixed equations, but by simple argument of charge conjugation symmetry and the flavor symmetries, we end up reducing the original Degrave equations into this same number of equations, but with only two flavors that mix with each other. All the other flavor combinations decompose in terms of evolution. And then the next question is, how about the kernels? And although we have written these forms in these 7 independent one, and the question that you may have is, are they all independent or are they all non-zero? And this is something even more beautiful, and I want to spend some time telling you about this, but I want you to first think about this. The first question I want to give you is, which kernels of these 7 ones are non-zero at the leading order? And what kind of diagrams that give these kernels? And I'll give you 1 minute. Feel free to discuss with your classmates. And any questions? Okay. Yes.
I'm confused about this question. So how would the kernels nullify at leading order?
So the kernels are the evolution kernels. They are calculated order by order in perturbation theory. Yes, so they are results of the UV renormalization of PDF.
Yeah.
So the best way to look at this is to simply draw some perturbative PDF diagram and look at how the flavors can mix with each other. And then you get an idea about how the kernels arise from UV renormalization. I did not tell you much about the how UV is actually renormalized, but this physical understanding something very simple. It doesn't care about all the technicalities of the renormalization. So just draw some fun diagrams.
Because the splitting functions are just for diagrams of one vertex, so that's the way that we should see it.
At the leading order, yes. Yes.
Yes, yeah.
So if you have thought about this and if you want to share what you found, please feel free to raise your hand and share your thought. And if not, I will go on and tell you the result.
I actually think that also has a anti-quark gluon. I think that would require like a third, three-point vertex.
First polymer doesn't have anti-quark.
First has either anti-quark, anti-quark.
Okay, so here is the result. At leading order, it's relatively simple, although the diagrams may look complicated, but they are actually not so complicated. It's just that I had a lot of lines labeling the momenta and a lot of gluon lines make it look complicated. At the leading order, you should have 4 kernels. And the first one is you have a quark split into a quark, and this gluon is integrated out. It can be virtual, it can be real, it can be real. And this from quark to quark doesn't change the flavor of the quark. So we have the valence splitting from quark to quark. That gives the first kernel here. And for the gluon, it's just from gluon to gluon and nothing complicated. So it's the kernel, the last one, G to G. And we can have gluon split into quarks or gluon split into Q bar, and they are the same as we have seen by charge conjugation symmetry. So this is the PQG, and that's a kernel here. And you can also have the quark split into a gluon and a quark. This is the kernel here. So this is the PGQ. This is what you get at the leading order. And we'll talk about the phenomenological aspect later, but for now, I want you to think about for the other three kernels, any of them are generated as next to leading order or alpha S squared order. If you have two splittings and you have 3 minutes to think about this. And feel free to ask if you have any kind of questions. Yeah, the reason I give you 3 minutes is because it's not so simple. So you need to think hard about this.
Leave more, you would also know. Let's see how you how would you get, or sorry, Q, no, Q bar, similar, but not Q, Q bar.
Oh, guys,
No, this one. They don't understand how it happens.
it would be like if you have a gluon splitting into QQ1.
You would have that vertex, right, but then would that be, you'd have to have gluon splitting the QQ bar, I know, but I see what you're saying, but how would it?
The Q.
You just get like a thin head.
Would be
So, yes, QQ bar.
Yeah, but then what, is my question.
might recombine the
Yes, QQ.
That would still be,
this would be QQ.
that would be next to next leading or higher order. Maybe I'm
Continuing on.
maybe wrong. No, this is only next to leading.
Level. Like, PQ bar.
When you have two.
That should be.
Like.
Wait, no.
You have like two independent vertices there.
My gluon splitting. Yeah, so we have a gluon. Gluon. I'm not sure what this is a QQ bar. Yeah. Yeah, because it's radiation exposure.
Could the resulting hadron.
There is no violation of
Technologically be totally
well,
yeah, I mean, I guess it would basically be just a virtual hadron, like a region. As opposed to, it's just the exchange. A virtual exchange. I'm saying that that's what that is. The diagram is.
For sure. So it's not like a
Okay, so 3 minutes.
Oh, I know, but I'm saying.
Anyone wants to share? Okay, if not, I'm going to show the result.
Oh, you could have. Sorry.
So here's the result. Because we already have the other four splitting kernel at the leading order. So they, of course, they stay at next to leading order, but next to leading order are not so important compared to leading order. What we are interested in is whether any new kernels arise at next to leading order, which are 0 at the leading order. So let's start with something simple. We can have a successive splitting, 2 gluon splitting for quark to quark. And these 2 gluon can cross. And they don't change the quark flavor, so they still contribute to p valence quark to quark. And for the C quark splittings. If we have a quark that first split into a gluon, and this gluon further splits to quark and antiquark, or this gluon splits to antiquark and quark, these two diagrams contribute to PQ to Q of C contribution and PQ to Q bar of the C component. So we have these two kernels that arise in one loop, two loop order. But for the other one, PQ to Q bar valence, anybody has thought about this diagram? So this diagram, it looks weird, but it's there. It's a quark that first splits to a quark and a gluon, and this gluon further splits to a antiquark and a quark. But this diagram interferes with another diagram in which you reverse the momentum of these two, reverse the two quarks on the right-hand side of the cut. And this crossing, the quark line does not break, so it doesn't change the flavor of the quark, but it's from quark to antiquark, so it contributes to p-valence, quark to antiquark. And therefore, at this order, all the 3 0 kernels at the leading order arise. But we have a degeneracy. This degeneracy is for Q to Q and Q to Q bar, C contribution, C component. So this looks very natural, right? Because a quark cannot go to other quark flavors without a gluon. But from the gluon point of view, it should not care about which flavor it splits into, right? But the next question is, does this degeneracy retain at the next order? So we go to next to leading order, or alpha S cube order. And the question is whether these two kernels labeled in blue, whether they still stay equal to each other at next to leading order. And you have, yes?
Elaborate a little bit on how that probably to like the C quarks, or like, or what's the these are like C quarks in particular. Where is the?
So C quark, what it means is it doesn't care, it doesn't depend on the flavor of the quark that it's splitting to. So in these two diagrams, the upper quark, it can be of the same flavor as the lower quark, but it doesn't have to, right? That's what we mean by the C splitting. So yeah, please, 3 minutes to think about this, and feel free to discuss with your classmates, and feel free if you want to share what you think. This is not easy. This is 3 minutes. This is not easy. It's okay. You don't get it in 3 minutes.
Just generous. I assume that refers to like Feynman diagrams that are topologically.
You know, let's say
so just a trick, because usually one is used to seeing Feynman diagrams like that notation with that it looks like everything is like
we use it too.
just the same. It's kind of more difficult to read because you don't have like the time flow.
You should still have the
process more.
You still have to separate out like some procedures, like.
Okay, so
You know, maybe it's like ladder diagrams, I guess. It's sort of like similar, like
that's leading.
broken ladder diagram. I don't know. It's just like same different
One
dynamics.
Leading on. Not blown, more vertex. These are the vertex. Right? So here you have two. So this is NLO. NNLO, just something like this. Oh, it should be a gluon. Shit, that's why you were confused. Notice that.
I mean, it's the same like 3 gluon vertices, right? And sorry, same like the With two carpets, it's the same like vertex, it's just.
Have another
The gluon exchange across the. Parts of the laddering, that so to speak.
and then low and then low.
Uh,
I think it's like if you like break off the glue on.
So if you look here.
Yeah.
On the other, kind of topologic.
We need another vertex,
you can
but
isolate
for what I'm seeing, that's diagrams
of,
it's just counting the order of vertices side.
you know,
This
that's gonna work, then you have to make.
Low and
So the per,
This is like.
so in this case,
and well, this is QQ.
like this, so it's P.
So, I mean, the initial.
We're not counting the vertices here.
That's coupling.
So you would have a bar go out.
Okay, so anybody wants to share? Yes.
I guess my idea was that you can have just like, you know, for like next to leading order.
And then
Yeah, or no, never mind, that would be next to leading order. Or was written off.
like
Oh, no, but there's four vertexes here. Oh, I'm sorry.
it would be C.
So if not, I'm showing the result. Again, because all those kernels are already there, we only care about the diagram that may break the degeneracy between the C splitting of Q to Q, Q to Q bar. So we take from the previous diagram, as shown here, a two-loop order, but we add another gluon. And this gluon is a virtual gluon. It's not cut. It's a virtual gluon. And this is a next to leading order. And again, the first diagram, it doesn't care about the flavor, whether these two quark flavors are the same. So it's contributing to the C splitting of Q to Q. And the other one, by reversing the upper fermion arrow, is from the C splitting of Q to Q bar. But are these two diagrams are the same? And this is what makes it so non-trivial. In QCD, we can label the color indices of all these vertices. And the gluon is color diagonal. So AA, BB, CC. And on the right, we have CC, BB, AA. I just referred the order. And then you see each quark loop gives us a trace over the color matrices. The first one is TA, TB, TC. And the bottom one is TC, TB, TA. But on the right, we have TA, TB, TC on both up and the down parts. And then you can work this out. You notice that for the first one gives you the DABC squared plus FABC squared, but the second one gives you DABC squared minus FABC squared. So whether these two diagrams are the same or they sum up to 0, at least they are not the same, right? They are different. But whether they have overall sign differences, and that's indeed the case, because in the first diagram, it is the anti-quark line that's being cut. But on the right, it's a quark line that's being cut. And the cut anti-quark line introduced the extra minus sign. So the first diagram contains the extra minus sign, which gives the minus sign here. So if you take the difference between these two diagrams, which gives us the difference between the two kernels, and this gives us something proportional to DABC squared. And as you know, DABC is that's another structure constant of the SUNC group. But what's interesting is DABC is different from FABC because it's not 0, even in abelian theory. So this effect is actually not a non-abelian effect. This is an abelian effect. But what makes it non-trivial is that it's a quantum interference effect. So on the left, we have two gluons exchanged, but on the right of the cut, we have only one gluon exchange. So this quantum interference breaks the degeneracy of the C splitting from Q to Q and Q to Q bar. And this is something very, very non-trivial. And it's slightly counterintuitive because it's against our classical thinking. But this degeneracy is broken starting at next to leading order, and due to this quantum interference. So now we have seen that all these 7 kernels are non-zero and they are not equal to each other. And then let's ask, with those knowledge, what should we expect? Does that tell us anything about the magnitude or relative values of all these different PDFs? And what phenomenological effects does the deglap evolution bring? And let's again start at the leading order. At the leading order, we only have these 4 kernels, and I'm sure you have seen this multiple times. We have gluon to quark, quark to gluon, gluon to gluon, and quark to quark. But the last one is only for the valence splitting from quark to quark. And with these 4 kernels, the deglap equation look very simple. You see, the quark only mix with quark; they don't mix with anti-quark. Anti-quark only mix with anti-quark, but they don't mix with quarks. And both of them mix with gluon. And for the gluon, it mixes with gluon and the singlet combinations of all these quark and anti-quark PDFs. And now, let me tell you something useful. When you think about the deglap evolution, what you should generally expect. The convolution first is defined in this way. And if we have X for the whole thing, this is a convolution of the 2 factors, P and F, P at Z1, F at Z2, and Z1 and Z2 should multiply to give X. And therefore, the left-hand side on the evolution is related to the kernel and the PDF on the right-hand side at Z1 and Z2, and both Z1 and Z2 are in the range from X to 1. So the change of PDF at the point X is related to the kernel and PDF in the range to its right. And now let's see, if we imagine X is very large, then, by the way, the first thing is both the first 2 kernels are positive. And so they tend to increase the PDFs. But if we look at the large X, and large X is dominated by the other 2 kernels, because the first one, these 2 do not have singularities when Z goes to 1, but the other 2 kernels have singularities when Z goes to 1. And if you push X to large, this is related to the kernel and PDFs at the large X region. And these 2 singular pieces are both negative. So at large X, we tend to believe that the PDF will be decreasing as you evolve. But at a small x has some singularities, say 1 over Z here and 1 over Z here. And these small x are positive. They give positive contributions, and they will make the PDF increase at small x region. So generally, we should expect that the evolution brings the PDF from large X region down to the small x region. And this is indeed the case. If we look at the global fit result here, this is a PDF global fit by the CTEC group in the year of 2019. They call it CT18 PDF. And on the left-hand side, it's a 2 GeV PDF. On the right-hand side, it's a 100 GeV. And this from the left to the right is obtained by solving the deglap evolution equation. And this is all the flavors are laid together. And if you just compare by eyes, you see that the large region is pushed to the small x regions. And I add some grade. You can compare that, for example, at x equals 0.2 for this blue line is the U quark. You compare the left with the right, you see it's decreasing at large x, but at small x, clearly it's increasing. And that's a general expectation. And this property, because it's already there at the leading order, it should not be altered by high order corrections. And what does high order do? High order effects as to give us a qualitative difference if qualitative changes occur. And we have seen that they do occur. What qualitative change occur at the next leading order is that we have 3 new kernels. The first is the C splitting from quark to quark and quark to anti-quark. And this means and they are equal. This means that if, say, we have a U quark can split into strange and anti-strange, or D to anti-down quark to anti-down quark, and they have equal probability to go to quark or anti-quark, and etc. And we also have another one, the valence splitting from quark to anti-quark. And this, if you look at this diagram, trivially, we can look at the color factor. And this color factor can be easily worked out. And you see that it's negative. So you have a negative color factor, but without the color factor, this diagram is positive. So we are getting a negative splitting of Q to Q bar just by the non-abelian feature. And what this means is something opposite to what we have above. What it means is that if, so because its kernel is negative, it only controls the splitting from U to U bar. And U to U bar is suppressed as compared to the U to D bar, U to S bar, etc. And the above kernel is that U has equal probability to go to DD bar. And what this means is that there is some flavor difference between the anti-quarks, because U bar and D bar are not the same. And D bar and S bar are not the same, because we can also have the D to D bar, which is different from D to S bar, etc. And we can be more quantitative by taking the de-Glab equation, and for example, by taking the difference between U and D and U bar and D bar. The previous kernel gave us these two terms, the PQ bar V, and the first one is saying that the U minus D is mixing with U bar minus D bar. And the second one is saying that U bar minus D bar is mixing with U minus D. Without these two terms, these two equations are evolving just by themselves. So suppose you have an initial condition at which U bar is equal to D bar, and then the evolution will keep U bar being equal to D bar at all scales. But with this mixing, it breaks this naive expectation. If we have U bar minus D bar even at the initial scale, evolution will break this equality. And an example is even here. Again, by the same set of PDFs, and this is plotting the ratio of D bar over U bar at the initial scale 1.4 GeV and at 100 GeV. You see that D bar is greater than U bar for a fairly large X range. And we can understand this from the equation here, because U bar minus D bar is mixing with U minus D. And we know that in PDF, in the PDF of proton, U is greater than D. So this U minus D is positive, but the coefficient is negative. So it brings down U bar minus D bar, and that makes D bar tend to be greater than U bar at large X region. And as the even further subleading order, we have these two diagrams which break the degeneracy of the C splitting from Q to Q and Q to Q bar. But again, we have a sum rule, and this is a conserved the valence quark number. And previously we have seen that the splitting probability between U to S and U to S bar are the same, but now this is broken. They are not the same. And we can see this more definitely by looking at this equation, by taking S minus S bar, and de-Glab gives us this. We have the first term is QQV minus QQ bar V convolutes with S minus S bar. This term evolved by itself, and we already have this before. What's new is the second term. This gives the non-zero mixing between S minus S bar with the non-singlet contributions. So we should generally expect that the strange is not equal to anti-strange, although their integrals for x from 0 to 1 is 0. And similarly, C bar is not equal to C, and B bar is not equal to B, even though naively we should picture them we normally picture them as the same in the proton. And this fact was first realized by Catani et al. in this paper in 2004. And the interesting thing is they were not the group of authors actually doing the calculations for the next to leading order kernels. But after the next to leading order kernels were published, they noticed that these two kernels are different, and that then led them to make this conclusion. And this is something highly non-trivial. And so we concluded that all or naive flavor symmetries of PDFs are broken. And then because they are broken at the perturbative level, there is no reason that they should be reserved by the non-perturbative physics. So at the initial scale mu0, when we parameterize all these PDFs, there is no reason that we should parameterize them in the same way. But that said, in actual fate, you can parameterize different flavors in all different ways. But if you have no data to constrain them, you get a lot of flat directions in your chi-square space. So you need data to constrain and separate all these different flavors. And that's where physics of the processes that come in. So now the first question I want you to think is, how do we separate U from D from a physical process? I mean, the PDFs, they all enter the physical process in the same way, right? But suppose now you perform an actual global fit. You want to parameterize U in different ways, but you need data to constrain these two parameterizations separately. So what kind of data can help you separate these two contributions or these two flavors? I noticed that it's already 5 minutes over time. But Alberto just told me that time is a little bit flexible in this session. So before going on, I wonder if you have any questions. So please feel free to ask. And this is the second to last slide, so it won't take too long. But if you have any questions, feel free to ask. And if you have no idea what this question is asking, also feel free to ask. So please raise your hand and tell me all I have just said is nonsense. It's okay.
Good to probably, yeah, so you change the target such that the relative contribution of U and D's, things.
Charge separation,
Some processes.
charge separation,
Please, if you have questions, feel free to ask.
right up and down. Using.
Huh?
Charge separation like up and,
Yeah.
is there any?
No, just some general, general.
So
It's like a proposal. You propose an experiment. You want to argue that your experiment is significant because it gives separate constraints on up quark and down quark PDFs.
you should play with the targets that you have available. For instance, if you have hydrogen that has a 2-to-1 ratio of U to D, and then that would give you like a probe that's more for U's than D's. So if you want to probe down quarks, you should pick a target that it has a higher ratio of D to U. That's how you.
Yes, great. That's what I'm going to say. But I see some question there.
Might be not the right answer, but I was thinking, can we use Pauli or Dirac form factor to separate U and D?
Sorry?
Pauli and Dirac form factor to separate U and D? F1 and F2, the Pauli form factor and Dirac form.
They want.
So I'm about to talk about that. So you want to separate U and D, generally we cannot just have one kind of data because one kind of data only probes the combination of all these different flavors. For example, we have DRS, we have F1, F2 structure functions. And this F1 and F2 are proportional to the charge squared weighted U plus U bar and D plus D bar, etc. So if you only have F1 and F2, you cannot separate U from D. And to answer your question, both F1 and F2 have these combinations. So they cannot be. So if you have both F1 and F2, you cannot separate U from D because they depend on PDFs all in the same way. But as this gentleman pointed out, if we have another kind of target, say a neutron target, we replace, by default, I'm talking about the proton target. But if we replace the proton by neutron, and where does neutron come from? Neutron can come from a deuteron. Deuteron is another kind of hydrogen nucleus. And deuteron is a state of proton and neutron. And there we can use isospin symmetry. We know that isospin symmetry tells us the U quark in proton is equal to D quark in neutron. So that replaces the U by D in the upper row and D by U in the upper row. So this gives a different combination of U and D. So with these two different kinds of data combined, we can separate U from D. But then you ask, but this doesn't differentiate U from U bar and D from D bar. And that's indeed another question. So how do we separate anti-quark from quark? That's another question. 1 minute.
We use pion targets for that.
Right?
Targets,
Pion?
pi plus, pi.
We generally don't have pion target.
Find targets.
So,
Something.
Like, but we too could have exclusive reaction where the interaction is happening with the pion.
yes, we can have pion target, but we are more interested in proton PDF. And pion PDF is not simply related to proton PDF. But it's true. In fact, you can have pion beams from a secondary beam experiment. Yes. Yeah, all we are doing here is to look at this, the proton PDFs for all different flavors. Yes. Any thought?
Taking ratios between multiplicities.
Multiplicity, for example.
So let me think.
Yeah,
Well, having an antiproton target.
really have
Yeah,
that.
exactly. You can have an antiproton.
Yeah, I mean, it's not very common, I think, but you could do it, right?
You can do it. And in fact, the Tevatron, the experiment at the
Ah.
Fermilab in about 10 or 20 years ago, Tevatron is a collider of proton and antiproton. Yes. But here, we only talk about DRS, right? DRS is a collider or fixed target experiment of electron and proton, electron and the nucleus target. So we are not at there yet. And there was no, as far as I might not be correct. It's an electron colliding with antiproton. I'm not sure if there was such an experiment. It could be, but I don't know. But the normal way to separate Q from Q bar, they are, again, not a unique way, but there are some major ones. We can look at we go beyond the DRS. We look at the hadron collisions. And the one process is the Brillouin production cross-section. For example, you have in LHC, you collide two proton beams and you produce a W plus, W minus, and Z boson virtual photon. And this then decay into a lepton pair. But they are all produced by the collision of quark and the anti-quark. So we get various combination of quark and anti-quark. And these two flavors doesn't have to be the same because for W production, you are mixing with up and down, up and U and D bar. But for quark, for photon and Z production, we have UU bar, DD bar, but they all give constraints on the anti-quark PDF. And another one you can have is for the DIS structure function, F3. F3 is a parity violating structure function. And there it depends on U minus U bar, D minus D bar, instead of U plus U bar, D minus D plus D bar. And this, by combining all this, we can hopefully distinguish U bar from D bar. And what about gluon? Gluon is very important in PDFs, and that's one major knowledge we have gained from the global analysis in the past years. We learned that for a fast-moving proton, about closely a half of the energy, half of the momentum is carried by the gluons. They are not carried by the quarks, not by the antiquarks, they are by the gluons. So gluons constitutes a major portion of the proton, but how do we constrain them? And by constrain, I mean constrain gluon with fairly good precision. So it's true that at DRS, gluon also contributes, but gluon contribution is next to leading order, so they are generally suppressed, which means for a given experiment, the gluon PDF uncertainty you will get is a little bit large. So generally, we want this gluon to appear at the leading order. So at the leading order, how do we have gluon PDF? Any idea?
Add a proton at very, very high energies to try to touch the gluons inside, but I don't know if that would be at leading order.
So is to look at the jet production. At hadron colliders, most of the events will be jet production. A lot of jets are produced at hadron colliders. For example, if you look at the LHC website, they have assembled the total cross sections in order, and the first one is always the jet production. The reason is QCD is much stronger than electroweak, so always you produce jets, and the major background is also jets. But if we look at the jet productions, we select the inclusive jet events, and a major portion of those jets happen by the collision of quark or anti-quark with gluon. And the reason I put quark here is because quark PDF is greater than the anti-quark PDF. But the gluon PDF is also important, so it contributes to jets. And it turns out that jet productions is the major source constraining the gluon PDF. And so now we have up, down, U bar, D bar, and gluon. We have some more. So we have strange quark. How do we probe strange quark? And this is something even more complicated. And because we have argued before that strange quark should not be zero and should not be the same as anti-strange quark. But I see that time is already up, so I will omit this 2 minutes, and I will directly tell you the more or less partial answer. And this is still an ongoing effort. And there are a lot of PDF fitting groups, they try to constrain the quark, strange quark, and try to distinguish strange from anti-strange, but this issue is not settled yet. And the major issue is about precision, because we have some old data from as you can see, the paper I'm citing is 2001. This is a group that performed the NewTEV experiment, which is a collision of neutrino and nuclears. And this neutrino is exchanging of charged current, W plus or W minus, with the nucleus, and then turns into a muon. So you can observe this muon. But we can also select the final states here. So that if we want a strange quark here, strange quark with a W plus will give us a charm quark, and charm quark can decay into a muon. So we can look at the dimuon production. This gives us constraint on the strange PDF. And if we use neutrino, we'll hitting on the S strange quark. If we use anti-neutrino, we'll be having anti-strange. And if we have precise measurements of both, we will be able to distinguish S from S bar. And if we don't have that good precision, we can only say something about the strange PDF being non-zero. And the further discussions are for the W plus charm production, and you can tag a charm jet at hadron colliders. And another way is, as proposed by the GEM group down here at Jefferson Lab, is to select the final state flavors by looking at a particular hadron, like a kaon. Kaon contains strange quark, but if you look at kaon, you introduce another kind of non-perturbative function called the fragmentation function. So GEM group proposes to simultaneously fit PDF with fragmentation functions, and that effort is still ongoing. And of course, you can always have constraints from lattice QCD calculations. And so this is an incomplete list. If you think about something, think of something new, you can contribute to this area. And to summarize, so this is the last slide. What we have done is we disentangled all the flavors from the de-Glab evolution equations, and we have seen that there are 7 independent, non-zero and independent kernels. And this, I hope you have learned something from doing the exercises. And this is a very non-trivial because it's a great example of first how the high order corrections bring qualitative changes to the leading order or low order predictions. And this occurred because some of the kernels are 0 at the leading order. And those are 0 just by accidental symmetries, not by real symmetries. So high order correction generally breaks them. And second, we have seen how the perturbation theory guides us when we make non-perturbative modeling or parameterizations of the PDFs. So this is an example of how perturbation theory guides our non-perturbative intuition. And because they are already all non-zero and independent at next to leading order, if you perform a further high order corrections, they are only expected to give quantitative changes. So the behavior we have seen should be very robust. And we have also seen how this plays a role in actual global analysis. And thank you very much.